Alright, so in this video, we're going to look at several miscellaneous topics, just several kind of things that we haven't touched on before, or maybe we've touched on parts of it. I just kind of threw them all together here. So a lot of the topics too in this part I've seen maybe in like a question or two in various parts of previous practice tests, or the free response questions. All right, so our first topic we're going to look at is alloys. So I'm sure you probably heard of alloys before. So alloys are going to be mixtures of, generally it's metal-metal mixtures. Though sometimes like alloys such as steel could use carbon in them, but alloys are generally metal-metal mixtures, okay? And there's lots of examples of alloys in your everyday lives. So if you've played a brass instrument, brass is an example of an alloy that is a mixture of copper and zinc atoms. And then another common example would be a lot of your coins. So are made of alloys, or are alloys themselves. Or like I said, steel too is another example of an alloy that uses these three metals, iron, nickel, and chromium, and then also they'll throw in carbon atoms too. All right, so two types of alloys that we're going to look at is one in which the atoms of the added component or components are going to take up spaces that are equivalent or about the same size as the spaces that the host metal would take up. So those are referred to as substitutional alloys. The other type of alloy, which is an interstitial alloy, is ones in which the host metal is going to be larger than the additional atom that's being added in. And the additional atom being added in is going to fit in between the spaces of the host metal. So first type, substitutional alloys, again, these are going to be formed when the additional atoms are going to take up equivalent spaces as the host metal. So for substitutional alloys, to predict when a mixture would form, like when an alloy mixture would form a substitutional one, you would need to know the size of the atoms or their relative sizes. So if they're pretty close to each other on the periodic table, like in the same period, pretty close to one another, they would likely form a substitutional alloy. Sometimes they might, in the question, actually give you the size of their atomic radii. So example of a substitutional, which I mentioned a few minutes ago, is brass. So if we're looking at brass, its primary or host metal is copper. So the copper atoms are represented with the brown circles here. And as you can see, zinc, which is really similar in size to copper, and if you were to actually look at their placement on the periodic table, you'll see that they're in the same period right next to one another. So we can assume that they're probably about the same size. So zinc, which is represented with the pink circles here, is replacing some of the copper atoms. So it takes up the same space or equivalent spots as the copper one. It's been substituted in for a copper. So that's substitutional. Okay. And then on the other hand, interstitial alloys, in these cases, one of the atoms, so the host atom, the main atoms, is going to be larger than the extra atoms that are being added in, because the extra atoms being added in are going to fit in between the spaces taken up by the host atoms. Now, forming these interstitial alloys would cause the substance to become, or not substance because it's a mixture, but it would cause the metal to become, or the metal lattice to become harder, stronger, more rigid, and less ductile, because there's less space in between those atoms, so it causes the metal structure to become more rigid. So here's an example of an interstitial alloy. carbon, which is going to be a lot smaller than iron. And if you were to look on the periodic table, you could predict that iron is going to be larger than copper because it's in the fourth principal energy level, whereas carbon just ends in the second period. So copper, which is smaller, will fit in between the spaces of the iron atoms. Here's another example too, showing, or just a couple other diagrams showing the difference between substitutional alloys and interstitial ones. So again, substitutional, the atoms are about the same size, so they take up equal spaces. It's the substituted atom literally replaces the host atom. In interstitial alloys, the additional atom or atoms are going to kind of fit in between the spaces of the host metal. So again, since it's fitting in between these spaces, there's less space in between these host metal atoms, so it causes the interstitial alloys to be rigid and stronger and less ductile. All right, so that was alloys. The next topic we're going to look at is bonds and different types of bonds. So based on different properties of solids, you can identify the type of bond that the solid has. So first type of solid bond we'll look at is metallic. Metallic bonds, the key giveaway for them is that they'll conduct electricity as a solid. And the reason for why they can conduct electricity as a solid is that around metal atoms, there's what's called a sea of electrons, or a sea of mobile valence electrons. What that means is, so these little positive charges here are the nuclei of this metal. And so we have, around these nuclei, we have these valence electrons that are free to kind of move about. They're not specifically assigned to one of these nuclei, or one of these nucleus, or a nucleus. Instead, they can move about between all of these nuclei. And so since you have free moving charges, right, free moving negative things, that allows them metals to conduct electricity. Now, ionic compounds, on the other hand, won't conduct electricity as a solid, but they are going to be soluble in water, and they will conduct electricity once they're in water. The reason for that is, let's say we are looking at, say, sodium chloride. We have an ionic compound. When it's a solid, it's not going to conduct electricity, whereas when we dissolve it in water, you would have these ions that are now free to float around. And so now we have free moving charges. So now that an ionic compound, once it's in aqueous, can conduct electricity. Okay. Now, your covalent compounds could either be a covalent network or a molecular solid. So primary difference between them is going to be their melting points. So covalent networks are going to have, they're more in these rigid lattices. They're going to have higher melting points, whereas molecular ones would have lower melting points. But both of those are going to be non-conductive. So an example of a question you might be asked where you would need to use this information is, suppose it says you're trying to identify the bond or the bond type of some unknown substance. And say you're told that it doesn't conduct electricity as a solid, but it is soluble in water, and it does conduct electricity once dissolved in water. You would then be able to identify, okay, if it's not conducting electricity as a solid, it can't be metallic, but it is soluble in water, so that tells us it's probably ionic. And then if it tells us that it conducts electricity in water, that's definitely going to tell us it's ionic. Right, and these covalent networks and moleculars aren't going to be conductive because covalent compounds aren't ions, right? They're not charged species. Ionic compounds does consist of cations and anions bonded together. So there are charged species there. And again, metallic conducts because those electrons are free to move about. All right, so next topic is vapor pressure. Vapor pressure is some topic that, or some term you might see when asked a question related to intermolecular forces. So the vapor pressure of a liquid is going to be the equilibrium pressure of a vapor above its liquid. So what it does is it looks at the, say we have some liquid and it is being vaporized. So when it's in this equilibrium kind of state, what that looks at is, if this is in a closed container, when we start vaporizing some of that liquid, at some point, those vapor molecules or atoms are going to recondense and reform back into the liquid state. So the vapor pressure is when the rate of the vaporization of that liquid is going to be equal to the rate of the condensation of those gas particles. All right, so again, vapor pressure you might see with a question related to intermolecular forces. And the vapor pressure is going to be inversely related to the boiling point. So remember we said before that the higher the boiling point, the greater the intermolecular forces, the stronger the intermolecular forces. So high boiling points is going to correspond to low vapor pressure, which means strong intermolecular forces. Whereas low boiling points would correspond with high vapor pressure, which would indicate weak intermolecular forces. So for vapor pressure, the lower the vapor pressure, the stronger the intermolecular forces. All right. So next topic is Morse potential curves. These curves, they kind of look funky, and I'll show you some examples of these curves. But what it does is it shows the potential energy between two atoms versus, so potential energy would be on the y-axis, versus the internuclear distance, so the distance between the nuclei of those atoms, and that will be plotted on the x-axis. Usually these curves are used for diatomics. And on these curves, you're going to see these wells. The well is going to be like a minimum. It's going to be where it dips down. And where you have those wells, the minimum energy, is where those two atoms would form a bond. And the deeper the well, the more potential energy that bond is going to have. So, question for you all. Which types of bonds do you think would have a deeper well? Single, double, or triple? Hopefully you thought triple, right? Triple bonds have more energy, so we would expect them to have greater wells. All right, so here's an example of those potential curves. So again, energy on the y and internuclear distance on the x. So what these curves look at is it's like a balancing act between when the two atoms are too close versus too far apart. And where they're just the right distance from one another is the bottom of those wells, okay? So when they are too close to one another, the electrons from, the valence electrons from those atoms are going to want to repel one another, okay? Whereas when they're too far apart, the nuclei of each of them don't feel any attraction to the other's valence electrons. So it's again like a balancing act between being too close or too far. Here's another example. Again, too close, those electrons in each are going to repel one another, but too far apart, there's going to be no attraction between nucleus and the other's valence electrons. And then where they're distance is optimal is where you'll have the well, and that tells you where they will form the bond. So that's how far apart they will be to form a bond. All right, next topic is kinetic energy. And we've talked about kinetic energy before, and if you'll recall, the average kinetic energy of a gas molecule or gas particle is proportional to what variable? Hopefully you said temperature, right? So, and specifically it's Kelvin temperature. So we have talked somewhat about kinetic energy, but we haven't really done a calculation to find the kinetic energy of a gas molecule, but you can find it using this equation here, which is on your all's reference sheets. So kinetic energy is going to be equal to 1/2 times the mass, and the mass of that gas molecule or gas particle in these cases needs to be in kilograms if you're wanting your kinetic energy in joules, or if you use grams, your kinetic energy is going to be in kilojoules. So 1/2 mass times the velocity, so how fast it's moving in units of meters per second, and that velocity term is going to be squared. All right, so final topic in this video is this idea of transitions and absorption spectrum. So 3 types of transitions we can look at here are electronic, vibrational, or rotational. The electronic transitions are going to be more energetic than vibrational ones, which are going to be more energetic than rotational ones. So that being said, which of those 3 types of transitions do you think would have the largest frequency? So which either electronic transitions, vibrational transitions, or rotational transitions do you think corresponds to the largest frequency values? Hopefully you said the electronic transitions, right? Because we know that E equals H nu. So more energy corresponds to more frequency, greater frequency. So electronic transitions have the greater frequency of these 3, and then which of those would have the greater wavelength? Hopefully for that one you said rotational transitions, right? Because frequency and wavelength are inversely proportional. So that means the greater the frequency, the smaller the wavelength, or vice versa.